Welcome. In this video, we're going to talk through two objectives. One is how to determine the sign of entropy change for a reaction, and then how to calculate the entropy change for a reaction. So in order to figure out whether entropy has increased or decreased in a certain process, we should be looking for these 5 things. So these are 5 examples of things that will cause an increase in entropy. So one is the increase in the number of moles. So if you look at your stoichiometric coefficients and you notice that you have more products than reactants, then your entropy is probably increased. I should also say the reverse is true. If you have fewer products than reactants, then your entropy is decreased. Other things that will cause an increase in entropy is going from a solid to a liquid, or going from a liquid to a gas, and going from a solid to aqueous. And again, if you were to reverse these, if you went from a liquid to a solid, that would cause a decrease in entropy. So these are all things that would cause an increase in entropy. The opposites would cause a decrease in entropy. And then increasing temperature will also cause an increase in entropy. If you think back to our definition of entropy, 0 entropy is when you have a perfect crystal at 0 degrees Kelvin. So as your temperature increases from 0 Kelvin, you have more movement, more possible arrangements. That gives you more entropy. As you go from a solid to a liquid, liquid to a gas, or into an aqueous, that's going to result in more possible arrangements, more disorder, more entropy. So let's take a look at some examples of how we would apply this to some real reactions here. Does entropy increase, decrease, or does it maybe stay the same? So if you look at this first one, we're going from a liquid to a gas. So entropy is going to increase in this scenario. You're going to have a positive delta S. And if you think about why, these gas particles are moving around much more freely than they are in the liquid state. So you got more disorder here. In this example, you're going from an aqueous to solid. So that right there seems to be it's becoming more orderly. So there's a decrease in disorder. You're also going from, notice that we have 2 moles of reactants, but we only have 1 mole of product. So the way you can think of that is over here on the reactant side, there's 2 possible places where these particles could be. On the product side, there's only 1 possible place where we can be. So we've limited the number of possible arrangements. We've also formed this ionic solid, which is a very kind of rigid crystal lattice. So the entropy has decreased in this scenario. All right, let's take a look at this one. We've got, if we look at our reactants, we've got 7 particles of reactants. We only have 2 particles of product. So again, we've got fewer possible arrangements that those particles can take. So it looks like our entropy is decreasing. Something else we should notice is that one of our reactants is a gas, but our product is only solid. So we're also going from a gas to a solid. So that's also going to lead to a decrease in entropy. So if I were to calculate the value for the entropy decrease for this reaction, it's probably going to be a pretty large decrease in entropy. So we've got kind of 2 variables here that are making a big impact. All right, if we take a look at this one, you have 1, 2 reactants, and then you have 2 particles of products, and they're all gases. So this one's kind of hard to predict. So the entropy here is going to be about the same. So change in entropy is probably not actually exactly 0. That's pretty unlikely, but it's going to be fairly close to 0 because we're going from 2 particles of gas to 2 particles of gas. There's not a big change there. Looking at this one, you're going from a solid to a gas. This one represents what happens with a dry ice at room temperature here. And so again, we're going to see a pretty big increase in entropy here because your gases are way more spread out, moving around randomly, a lot more disorder there. And then this last one, we're going from 2 reactants to only 1 product. Again, we're also going from a gas to a solid. So this one's going to be a decrease in entropy as well. This one's kind of similar to reaction 3 up here. So that's how we would apply those things. We're looking at the number of particles before and after, and also the state of matter to help us predict whether that process is increasing or decreasing in entropy. And so we want to be able to do that, predict the sign of delta S based on looking at things like state of matter and how many reactant and product particles there are. We also want to be able to calculate the value of delta S using this equation, which is given on our equation sheet. So delta S, the change in entropy, is the sum of the entropy of the products minus the sum of the entropy of the reactants. Notice the way this equation is written. If the products have more disorder than the reactants, then the delta S will be positive, right? That means you've increased in entropy, you've increased disorder. So let's look at a couple of examples here. On this type of problem, you would be given a table of values. You would likely be given just a smaller table, like this were a test question, you'd be given a smaller table with just the relevant values. But you can always find these thermodynamic values. They're in the back of textbooks. There's various reference sheets. They're going to list the heat of formation, the Gibbs free energy of formation, and then what we're going to focus on right here, which is the entropy, which is in joules per mole Kelvin. Something to pay attention to with your entropy, how it's different from these other values, is one, it's in joules rather than kilojoules, so keep an eye on that. That'll be important when you're doing other sorts of calculations. And also it's per mole Kelvin, so that K stands for Kelvin. So we will see this in a later application here. Delta G equals delta H minus T delta S. We'll see that our entropy is multiplied by the temperature in Kelvin. So just pay attention to your units of entropy. That'll be important in some other applications here. So if we're going to calculate the delta S value, it's going to be products minus reactants. So I'm going to look up the entropy of my gaseous water, which is right here. It is 188.83, and then I'm going to subtract from it my liquid water, which is 69.91. And then I'm going to subtract those two, 188.83 minus 69.91, and I get positive 118.92. The units are joules per mole Kelvin. So there we go. So notice how my entropy change is positive. That matches our prediction. We're going from a liquid to a gas. It is more disorderly. So notice our gas has more entropy than the liquid state did. So let's go down, try one more example. So in this case, I'm going to take these products minus reactants. So I'm going to take 2 times my iron oxide, and then I'm going to subtract from that my reactants. So I'm going to go up there and check out these values. So my iron oxide is down here. So it's 2 times 89.96 minus 4 times, let's see, right here, I'm looking at the wrong one. That was gas. I need to look at there we go, it's solid iron. Okay, notice how solid iron has much less entropy than gaseous iron. And then 3 of oxygen gas, that's this one right here, 205. And if I stop and plug this all in my calculator, I should get negative 543 joules per mole Kelvin. So notice how this one has a pretty large and negative delta S value, because we're going from 7 moles of reactants to 2 moles of products, and we're also going from our reactant had a few gas particles in it, whereas our product only has solid. And so we're going to see a fairly significant decrease in entropy in this process right here. All right, so there we go. Again, what we want to do is we want to be able to calculate delta S given these values of absolute entropy that you could find in various tables. And we also want to be able to predict the sign of delta S based on a chemical reaction, looking at things like states of matter and the number of particles of products and reactants. Thanks for watching.